Yes, much better.
Okay, thank you very much. Hello, thank you, Cozy, for such a nice introduction, I would say. And so, Cozy already explained about my research topic, about my portfolio or bio. So I would not go into that. So currently, I am just working at a research DER power converter researcher at Electric Power Research Institute. And the topic that today we will discuss is mainly based on my PhD research. And I have completed my PhD this year, March. So basically, you could say that I have the feeling of being a student still yet, although I am working at every around 1 year from this year, January. Okay, let's move into the main topic. So basically, what we will discuss is how we can integrate reinforcement learning into power system. And when we think about power system, we have to think about inverter because the conventional power system is changing and inverter is integrating into the grid more rapidly than we think. So one of the challenge of that integration is the oscillation in the power system. So that we will see from these all of the events that IEEE PACE Task Force 80 recorded from 2009 to 2021. And based on this oscillation, we can see that the number of oscillations are getting prominent day by day. And if we look into the oscillation events in with respect to demographic area, we can see that China is actually expecting a more such subsynchronous oscillation, and USA is also, I would say, is increasing in that perspective. So this number is not just a number. This is telling us a story that China is actually integrating a lot of renewable energy and which are suspected to actually introduce oscillation into the system. And if we think about with respect to the frequency, what is the oscillation frequency? We can see that the most of the oscillation frequency that we actually observe over here is the subsynchronous, less than 30 hertz, 60 hertz in that region. Of course, there are supersynchronous oscillation as well, but subsynchronous oscillation is the more dominant. Okay, let me actually change my. Okay, so and because of the subsynchronous oscillation, and which is actually coming, which is suspected to coming more from the inverter-based resource, it is getting actually important to analyze this oscillation. And one of the actually recent research come into the picture that this oscillation are actually coming from many cases, weak grid scenario and inverter resources and radial connection. And when the oscillation comes from weak grid scenario or oscillation comes from other sources, there are many ways to mitigate this oscillation. And one of the way that actually we will investigate in this presentation is to tuning the inverter control gain. When we say we are going to tune the inverter control gain, there are many ways to tune the inverter control gains, right? Conventional control system, optimization technique, as well as currently emerging method, deep reinforcement learning. And of course, there are pros and cons of all of these methods. So conventional control system assume that system is linear and it struggle to handle multiple control objectives. So this is the main um, bottleneck of the conventional control system, and which is not scalable at all. And there are few optimization techniques which actually can handle linear and non-linear system and as well as can optimize multiple objectives. But many of these methods are actually used for offline tuning. Because of that, Recent research is actually trying to utilize neural network or deep reinforcement learning based method to come up with a scalable solution to tune the inverter control gains. So there are many advantages over here. It can handle nonlinear system effectively, can tune multiple control parameters, and as well as RL can be actually trained in offline and online in both ways. And it is highly scalable. And I think everyone is familiar with the large language model and the scale of the large language model. So that means we can imagine that the scalability is not an issue for neural network based system or control tuning. So because of this, I adopted in my research to actually investigate further how to actually tune inverter controller gains to mitigate subsynchronous oscillation, or to come up with a better control gains using reinforcement learning. So that is the main focus that we will discuss moving forward. And for this experiment, during my PhD, I was doing internship at EPRI. So we have a funded project over here, which is called PICO Design Protection Inverter Co-Simulation Project. So this is the test bed that um, I worked on at that time, and also I collaborated with my PhD research to verify the control gains that we are getting from the reinforcement learning to deploy into hardware and verify the outcomes. And that was actually, I would say, fantastic opportunity for me to verify whatever we are getting from training directly deploy into hardware and see the result, and to see whether the hardware result as well as simulation and deep learning result align or not. So now let me move into the main topic that we will discuss moving forward is the reinforcement learning. So the journey of reinforcement learning actually started in 1950s with the invention of dynamic programming and Markov decision process. So Markov decision process is a kind of mathematical modeling to model any problem or any problem that actually has a many decision along the whole pipeline, and do that modeling in a mathematical way using this Markov decision process framework. And dynamic programming is the process of solving Markov decision process. And this Markov decision process is kind of model based. We need to know what is the system model in a mathematical way. We need to know the system states, we need to know the action space, transition function, discount factor, all of those things. Then 1980s reinforcement learning emerged, which is kind of model free. So the ideology is that we do not need to know the system model to learn something from the interaction between environment and agent. So basically, think about environment as a power system. An agent is something intelligent computer algorithm. So environment interacts with agent and provides two things. The first is the reward and second is the observation. And based on reward and observation, agent actually creates the action. Then based on the action generated by environment, it actually environment actually perform on that action and provide the feedback again to the agent. So this is kind of a closed loop system. And this is how the reinforcement learning or Markov decision framework works. And then another revolution was 1989, the Q-learning emerged. So Q-learning was kind of a breakthrough at that time, which is saying that when we know the observation states and reward from the environment, Q-learning can actually learn a lookup table. Based on that lookup table, it can generate action and environment can perform that action. Later on, 2013, deep Q learning was emerged. So basically, previously in the Q learning, we have a lookup table. Now instead of lookup table, a neural network is actually performing action based on the reward and based on the observations. And then later on, many good algorithms came into the reinforcement learning, proximal policy optimization, TTPZ, TD3. So those are mainly breakthrough in the field of reinforcement learning. And PPO, which is the proximal policy optimization, was PPO, which is the proximal policy optimization, was introduced by OpenAI. So I hope everyone can hear me, right? Let me check my.
Yeah, now, I can hear you, but sometimes, I lost your words.
I see. Okay. Okay, let me actually move on again. And PPO algorithm is actually introduced or proposed one of the scientists from the OpenAI, and it is kind of a breakthrough in reinforcement learning. So let me tell you this way: everyone uses ChatGPT or other large language model, and the reasoning capability that we see in those language model is based on one of the derivative algorithm of the PPO. So this is kind of one of the reinforcement learning algorithm which revolutionized the industry. Okay, now let's move into the inverter control tuning problem in this presentation. Think about a simple system. We have a simple IBR-based power system. One is grid following inverter, one is grid following inverter, and we have a simple load over here. So we want to model this system in a deep reinforcement learning environment. So after modeling, what we actually want to deploy those modeling parameters into hardware so that we can verify our system. So this is the problem that we will explain in this presentation. And when we want to solve these problems, so in the existing literature, there are many ways people are trying to model any power system related problem into deep reinforcement learning environment. So one is the native MATLAB environment. Second one is the Python environment, MATLAB plus Python environment, and completely native environment. So the challenge is that most of the electrical power system simulation software that we use are popular are in GUI based, right? So if we think about MATLAB simulating, that is also GUI based. If we think about other environment, PSCAD, that is GUI based. So the challenge is most of the reinforcement learning implementations are popular in Python environment. So it is challenging to actually integrate both. So when you think about native MATLAB implementation, that means we are implementing everything into MATLAB environment. So also, if we want to implement everything in Python environment, the challenge is that the electromagnetic transient simulation that we will be utilized in this problem are not present in Python environment. So because of this, it is difficult to develop the EMT simulation and work on that domain. So therefore, to accelerate the trading and all of the problem, I came up with a new problem, a new solution in this research is, what if we convert MATLAB Simulink model into dynamic link library and import that into Python environment, then run the training, use the popular Python reinforcement learning library. So these actually help me a lot when it comes to develop such model. So then let me go to the next slide. So think about that. I have actually simple power system model, the completely inverter-based power system model. So to convert that power system model into a reinforcement learning environment, I have to go through multiple steps. So if I explain this way, we have to go through 4 steps. The first step is we have to think about that, okay, this is our model. We have to decide whether we want to create a single dynamic link library or DLL file from our model, or we want to combine all of them. So after the decision, we have to define what is the output of the model, because we have to explicitly design the input output so that whenever we are exporting that model into Python, we can actually access those input output from the DLL function call. And then the next step is the DLL generation. So that is actually done using MATLAB Simulink default GCC compiler. And then I have developed a Python library that I will present next, which can actually call any DLL file generated from MATLAB Simulink and perform EMT simulation in Python environment. Okay, so here is one example. Maybe I will present a simpler example next. Okay, so that is the actually process of creating the environment. But still, one question remains. When it comes to tune inverter control gains, there are many ways that I reviewed in existing literature. So basically, when it comes to tune inverter control, we can do three ways. The first way is replace PI controller by a reinforcement learning agent. And the second way is, so basically we have a controller, which is the proportional integral controller. We can replace the whole controller using a reinforcement learning agent, because neural network can map any function by training. And the second approach is neural network can generate the adaptive gain for the controller. And the third approach is, what if we can design our existing any controller into a neural network way, then we will be able to tune the neural network parameters. So basically the idea is to, if we have a controller and if we design that controller in such a way so that the controller gains behaves as neural network weight, that would be easier and for any hardware to implement that, because neural network will provide me just the control gain, then I'll deploy that into hardware. But other two methods, for example first and second one, has the drawback of we have to implement neural network into a hardware constrained microcontroller, which is sometimes challenging for many microcontroller to calculate the neural network in a um, high-speed fashion, because we know microcontrollers are compute constrained as well as memory constrained. So because of that, this research I mostly explored how to actually tune the inverter controller just by generating a phased, just by modeling the PI controller as a neural network. Okay, so let me actually go through the process step by step. For example, think about the same power system that I'm explaining from the beginning, and then I can model this power system as a reinforcement learning environment this way. This is the simulation environment, and this is the reinforcement learning agent, which consists of multiple components, actor, critic, and there is also a trajectory which is actually collecting all of the information from a single simulation, then providing all of the simulation to the reinforcement learning agent, and it is updating the policy, and based on that it actually based on the policy actually actor is generating the action. So now you might think, what is actually action or observation over here? So based on your problem requirement, you can actually design what is your action. Okay, so based on your, I will come back to the question later on. Based on your problem, you can actually design the observations as well as design the action. So that actually completely depends on your problem statement. So think about that. This is a simple grid following inverter current controller, cascaded current controller. Okay, and we can actually design or retrofit this current controller as a neural network such a way that all of the control gains you can see over here work as a weight of the neural network. So what is the advantage in this mechanism? The advantage is that we can actually train this neural network so we can actually train this neural network through any reinforcement learning algorithm, such as, for example, PPU algorithm. And PPU algorithm, what it will do, it will actually tune all of those control gain as a neural network weight. So this is the advantage of converting any controller into neural network. And by this way, at the end of the training, we will be able to extract all of those weight and deploy into hardware directly. So this way, we do not have to deploy a high computing neural network into hardware. So this is the one way we can actually avoid changing conventional inverter or controller. For example, think about that. You have a bigger system. You want to identify thousands of control gains for many of the inverters, or you have a top level primary, secondary, other controllers. And how would this work? Hello. This work. Okay, and so basically you can actually design your whole problem in such a way so that you can actually design your whole system in a neural network way, so that if you design all of your weights, all of your gains as a neural network weights, you will be able to tune all of those weights by reinforcement learning algorithms. So this is the whole idea of fixed gain based reinforcement learning or inverter controller tuning. And this is what we adopted in this research, as well as we verified this method using hardware deployment. So basically, we have done multiple steps. We designed the whole system into hardware, then we converted the system into DLL, then we actually um, um, imported the DLL into Python environment, and then we actually did the training using reinforcement learning. Then reinforcement learning actually provided us the controller gains as a neural network weight. We deploy those neural network weight into hardware. This way, we were able to validate the idea of tuning inverter control gains using neural network. Okay, let me go back to the question from the audience.
Thank you, Dr. Das. So if you have any questions, please use chat window so that Dr. Das can read your questions. So so in the meantime, so you're showing the neural network. Is this like a physics-informed neural network?
So yeah. So basically, when you think about physics informed, you have to actually think about that we integrated the complete physics into the neural network, right? So basically, if you consider that this is not a conventional neural network that we experimented over here. So if you just think about this one, let me actually go to the reading mode instead of speaker view. So if you just think about this one, this is just a PI controller, cascaded PI controller. And basically it is not fully connected neural network. It is just cascaded PI controller for the grid following inverter current controller. So we just design this in such a way so that the reinforcement learning is considering this as a neural network, but inside the neural network, this is just a current controller of the grid following inverter. So with respect to that, you can see that this is just a physics inform. We also consider that what would be the maximum, minimum boundary or region of you can say that perturbation the neural network will be able to do. So we limited all those things considering the control objectives.
Thank you.
Okay.
Any other questions? So yeah, please, Dr. Das, please go ahead.
Okay, thank you very much. Okay.
If I may ask that question.
Go ahead.
I think it was stated in one of the slides that the gains can be updated in real time. My question is, how often are these gains updated in a normal operating environment?
Thank
And
you.
if I can continue,
Mhm,
as this particular algorithm
mhm,
been implemented in real time
mhm,
and tested on the physical system?
mhm. Okay, thank you very much for the question. Yeah, it is possible to update gain in a real time, but the thing is, like in this research, we didn't update the gain in a real time. We actually um, receive the gain after the training, then we deploy those gain into the hardware. But the thing is that for the power system, a lot of the decisions are critical, right? So because of that critical decision, maybe many power system or utility company will not accept the fact that neural network will be able to tune any gain in real time. So because of that, it is possible using the neural network or reinforcement learning based neural network to update the gain, and the frequency that you are asking, it also depends on the user preference. How frequent you want to actually update the gain. Yeah, go ahead, Syed.
Hello. I
If
posted my
if I
question.
if I may just supplement that with one comment,
Mhm, mhm,
there's another method that can be used very, very effectively,
mhm,
and in fact has been used, implemented not only extensively in the laboratory testing, but
mhm,
even is in operation in power systems on large generating units,
mhm.
and that is in using adaptive control
Yeah,
to
adaptive control. Yes.
update the controller continuously, something like 20 to 30 times a second.
Mhm,
So it can really track the operating condition of the power system
mhm,
and thus go on updating the controller parameters
mhm,
according to that.
mhm,
And it has also been not only for generating units as the PSS, it
mhm,
has also been, uh, I should say, implemented are shown very clearly that even it can be used to update the gains of the IBR.
mhm,
So maybe it's worthwhile looking into the adaptive control,
mhm,
and it requires no extra hardware.
mhm.
Thank you.
Yeah, thank you very much. It is actually a good insight. So the from my understanding that for designing such adaptive control, maybe we need to know the system modeling, mathematical modeling properly, right? Or the idea of reinforcement learning is that you can actually tune any inverter or any system based on the observation and based on the trial and error, and the agent will learn, or neural network will learn interacting with the environment. So basically, you can actually tune the controller, tune any controller of any model-free system. So that is the whole idea. So yeah, I understand that, and I also explained that the overall goal of moving forward or using neural network in power system research or tuning inverter control is one of the objective is to scalability, another objective is to handling the non-linearity. So moving forward, we believe that there would be a more robust or physics informed control learning algorithm will emerge, which will be able to safely tune this inverter control using neural network. That's my perspective, maybe in future, or you can say futuristic thinking. Thank you.
Thank you.
Yeah. Uh, okay. Another hand. Okay. Said, maybe yeah, you can go ahead.
All right. Yeah. So my question is actually posted in the chat.
Mhm. Okay. Let me check the chat again. Can you please can you please actually say your
Uh,
question again? That would be easier.
yeah, yeah. Can you hear me properly?
Yes, I can hear you properly.
Okay, okay, okay. Uh, you're tuning your PI controller gains through neural network. Okay, that's fine. Uh, my only concern is that okay, your training data
Mhm.
will be limited, right? So you will not be able to train your system properly for the entire set of scenarios that a power system can experience.
Mhm. Mhm.
So how will your trained neural network will be able to tackle unknown scenarios?
Mhm. Mhm.
Uh, using your proposed technology?
Thank you very much. It's a very good question. So first, let me tell you this way. I explained before there are three ways. One way is to replace the controller directly by neural network. That is not the approach we are actually exploring in this research, because in that approach, when you are training a neural network to replace conventional controller, there will be a lot of scenario where the algorithm didn't explore. In that case, the neural network might generate unexpected result. The second one was the adaptive gain, but this is like completely replacing neural network, or designing neural network in such a way so that it actually behaves like a neural network during training, but at the end of the day, it is just a PI controller designed to tune the inverter controller. So basically, in this method, it is actually experiencing all of the scenario that we are actually simulating during our training. For example, one of the comment that you mentioned is the dataset is limited. So actually, there is no dataset in this training. That is the first thing. Why I'm saying there is no dataset? When I'm running the electromagnetic transient simulation, for example, I'm running the EMT simulation of this simple network. Basically, I call it episode. One episode is the single run of the electromagnetic transient simulation. After when one episode is complete, it is providing those episode output to the neural network as a trajectory. You can see that this is the actually collection of a single episode. Then based on that single episode, the neural network is learning. And based on that actually learning, it is taking the action. So basically, what I'm trying to say is that if you have a 1,000 scenario you want to simulate in your model, you can do that. And based on the 1,000 scenario, you can actually train your inverter controller and finally come up with the gains that can handle or tackle all scenarios. So there is no limitation of data over here because there is no external data set over here. Uh, did I able to make you clear about that?
Um, I can have some more questions for you at the end of the lecture, but for now, okay. So you are once you get the gains, the KP and the KI gains, right,
Yes.
from your system,
Yeah.
you are just putting it in your
Order.
hardware,
Yes.
testing it out. Okay,
Yes.
that's fine.
Yes.
But did you try doing some power hardware in the loop simulations
Uh,
for this thing?
not
Because
this in this.
you know,
Not in this
you know
research.
the yeah, because the idea is that you have to eventually see whether your inverter is able to handle any sort of disturbances in a IEEE bus system, let's say, wherever you are putting your IBR, right?
That is actually a good
So
solution.
yeah, so checking it out in a power hardware in the loop is probably the best way to go about it, because otherwise you will never know, even with your system in the lab, that whether you are able to capture
Mhm.
or reduce any sort of oscillations that might be coming up from your power system.
Mhm. Yep. Yep. That is actually a very good idea. So this is part of my PhD research. So I did this, most of the work I did during the last year, and I couldn't able to actually explore further because I had to defend faster at that time at the end of 2024 and join EPRI. So I hope someone will grab my research from here and move forward. That is my expectation. Thank you very much.
All right, thanks.
Okay, so basically this is the mathematical all of the symbols that we need to know to understand how the reinforcement learning was designed under the hood. So basically, the observation set that I am actually showing in the last slide is that, so you can see that the observation set that my environment is providing to the neural network consists of these observations. Basically, it consists of the d-axis current error, integration of d-axis current error, q-axis current error, integration of q-axis current error, vd, vq, ild, ilq. So basically, they are the control input of the cascaded current controller for grid following inverter. And the action space is the output of the cascaded current controller of the grid following inverter. And the reward function is, as a researcher, we have to come up with a reward function so that the agent can get a good feedback from the environment that it is learning a good network weight, or it is learning a good gain parameter. So based on that, we have to come up with a reward function. So this reward function we are able to come up with after a lot of experiment and training. I will explain a little this reward function. So before that, let me show you the result a little bit. So based on the reward function, we can see that over the training of the 100 episode of this system, the reward function was able to actually come to a steady state and reduce the error of all of the control gains. So you might ask, what is a good reward? That might be a very good question. The good reward is when the reward is completely zero. Then based on this equation, we can say that there is no error between the current reference set point as well as the measurement. And so based on that, we can see that when the reward is zero, we can say that the reinforcement learning agent was able to learn a very good weight and was able to come to optimal point, or we can say that suboptimal, because in the reinforcement learning it is difficult to say which point is the absolute optima. And then you can see that this is the evolution of the gain throughout the whole training of the 100 episode that I extracted from the neural network weights over the training. And this is the Ki gain, this is the Kp gain evolution, and you can see that this is the band at the beginning of the training. Of course, there was oscillation of the gain. Over the training, it became saturated and came up with a good set of control gains. And then this is the EMT result of the real power and d-axis voltage of the grid following inverter output terminal at the initial condition. And this is the result when the training was done and deployed those gain into the inverter and generated the same set of results. And so what we can observe is that previously there was an oscillation, a transient, which actually lasts from 0.5 to 1.5 seconds. But after the training, when the agent generated the new set of gain, this actually reduced that oscillation significantly. We also deployed those gain into the hardware that I demonstrated previously and try to see what is the output when we are actually a new grid following inverter is injecting power into the grid and sharing the equal amount of power just like the grid forming inverter. And you can see that the hardware result was also stable and there was no oscillation observed. So now I want to explain another perspective over here is the explainability of the learning algorithm, how actually it is doing under the hood, what are the factors influencing over here. So to understand that, in the reinforcement learning, we need to understand two factors. One is the exploration and second one is the exploitation. Exploration is the actor which is trying new action or trying to explore the variables or and trying to actually part of the actions so that it can actually come up with this optimal solution. So these actually help agent to avoid getting stuck into a suboptimal strategies. So this actually happens at the beginning of the reinforcement learning training. When the agent has a good sense about the environment, how everything works, and based on the observation, it is confident about the decision, it prefers to use the non-action or non-strategies. So that state is called the exploitation. So now let me explain this exploration and exploitation with respect to all of the trajectory that we observe. So this is the graph. You can see the neural network, the KP weight. So basically this is one of the weight that neural network is learning over the training. and this is the Ki weight. And you can see this is the output of the actor network, which is the current controller output, which is driving the inverter, this one. And at the beginning of the training, you can see that standard deviation is 1. That means at the beginning, there was a high variation of the output. So basically, it is taking random decision or random output. And as long as the agent is actually getting aware of the environment, it is learning and confident, at the time, the output of the agent is actually being confident and deviation is reduced. So this point you can see that, okay, the agent learned very good policy, and based on that policy, we will be able to extract the control gains. The same thing we can actually observe from the actor output. All those things at the beginning, it is actually the concept that we explained, it is actually exploring the environment, and when it has a good sense about the environment, it is actually exploiting or using the non-environments. So maybe let's actually show you this scenario, how the things are evolving over the training of the 100 episode in this animation. So you can see at the beginning, there was a significant oscillation in the real power sharing between grid forming and grid following inverter. But as long as the training is approaching for the longer time, it is able to come up with a good set of control gains and stabilize the system and reduce the oscillation. So these are the all factors, mostly theoretical part, that in this research I explored. But there are so many technical parts under the hood which I had to develop to come up with this system of training inverter controller using a neural network, so that we can deploy those control gains in any conventional or old system as well as new system. But the thing is that under the hood, we have multiple process which consist of, when we have a MATLAB Simulink model, I had to convert that model into dynamic or DLL file. Then I had to come up with a Python code that actually able to read the DLL file, then perform all of the training, integrate GPU, create a complete set of new programming to able to do the training and deploy those hardware. So to do the whole pipeline, I was able to come up with multiple Python library, I would say open source library, that I will provide the link at the end of the presentation. So before that, maybe it is worth investigating how the whole process works, so that my whole goal is to anyone can replicate the whole process and move the research forward. Okay, let me go with the DLL generation. Think about that. You have a simple inverter model and you define all of those input output properly. And this is the inverter model, and you can see that I actually did the conversion of the variables so that I am able to make sure that all of the variables are same variable type, or double or single, whatever it is. So this is important, because when we read the DLL, we have to make sure that we are actually reading or writing the exact amount of data. And then there is a few settings we need to know to convert the DLL. That is, when we have a Simulink code generation, we have to select the system target file, we have to select the language standard, then we also have to select the compiler, which will be helping us to generate the DLL file. Then go from the embedded coder, then build, then it will generate the DLL based on the Simulink model that I have. So that solves our maybe 10% of our problem. But the now next challenge is, okay, now I have a DLL file, which I also have a complete C file that my Simulink model generated. Now, how do I will be able to integrate that C or DLL file into my Python environment training? So to do that, maybe I will go a little bit faster, since we are approaching the end of the seminar today. So if anyone has any question, I will address at the end of the my talk. And you can see that at the end, I have developed a library which is also open source. You will be able to get that library into my GitHub. So basically, this library able to read any DLL file generated from Simulink, and if you define what is the variable and what is the size of the variable over here, you can see, then you will be able to just call a single function and you will be able to simulate that DLL file into Python environment. So that is the whole idea of SimDLL. So basically, when you generate the DLL file from Simulink, you do not need to write extra layer of code to read that DLL file. You will be able to do that using SimDLL. And then I have developed another library which is called control-rl. So basically, the idea of control-rl to create the whole reinforcement learning environment so that anyone generated DLL file from the Simulink environment able to train that control gain or whatever the control objective he or she has using this control-rl open source Python library. And you also able to look into the library and example. Inside the library, I have a single agent example that you can explore and update or retrofit for your system according to your requirement or control objective, whatever control objective you want to achieve. So the required function that we need to implement multiple function, for example, set the input output and what is the input variables or parameters value, what is the way of resetting mechanism for the model that you are exploring. And if you want to see the plot of the output, you can also set this function. If you want you also have to implement the observation shape, which is the number of variables that your environment is providing the neural network, and a few other functions. So if you look into the example, those are actually distinctly clear. I also took few screenshot from the example that you will be able to look into the library. So for example, this is the Simulink library. You can see, and I created a DLL file for the Simulink library. And when I have a DLL, I can actually set the input output directly into using that library. So you can actually design according to your model, whatever model you are utilizing. But for this example, I have a command variable which has a 7 variable of float type. For the grid forming, I have a parameter variable which is a float type 15 variable. So basically, you have to define all of those type of variable and number of variables in each section. Same goes for the grid following inverter. Similarly, you can also map what is the output you are getting from this DLL into this library. So basically, this library dealt with everything apart from the fact that you have to provide or you have to connect your model with the library. To connect your library, you have to define the input output properly using the control-rl. And then this is the input variables. For example, for this grid forming and grid following inverter, I have to set what are the input variables I want to experiment for this example. So we have to set all of the common variables that you can see over here. You also have to set all of the parameters that I utilize in my model. Same goes for the grid following inverter as well. And this is the most important thing. Since this is a library, it has to have a way so that any user can connect any set of action or any set of action that the neural network will generate and connect with the environment of the power system. So basically, you have to provide the index of the particular command. For example, in this particular command, this is my inverter model. I'm saying that 5 and 6, command 5 and 6 will be generated by the reinforcement learning agent. Then my inverter will use those decisions from the agent and generate the observation and reward. So this is how we defined. And you can also define what is the boundary of all of your actions. And similarly, the next important thing is the reward that I explained before. Think about that. For this control objective, my objective was to reduce the oscillation in the output when grid following inverter started injecting power into the grid and sharing equal amount of power with the grid following inverter. So basically my goal was to grid following inverter current controller should follow the reference properly, and if it doesn't follow the reference, it will penalize using the Q1, Q2, all of those values. And there is also a smoothing factor over here that I consider. And the idea is to user has to design the reward function based on his control objective. So this is the how this function is actually implemented. You can see this into the implementation as well. And the next set is the observation. Observation is what the environment is providing as an input to the neural network or reinforcement learning agent. So basically at the end of the observation function, you have to define that this is the observation you will utilize during training. So when you have done with all of those settings, then you can utilize this control RL library to actually create a new environment for your controller and tune the controller or perform any control objectives. So basically this is kind of open-ended library you can actually set, or you can configure for any control related problem using reinforcement learning. With that, I want to conclude my presentation. I hope I did not cross the timing. So basically it is possible to tune inverter control using reinforcement learning and deploy that into hardware without demanding high computing. And also the control RL library that I open source, you'll be able to get it from this link. You can actually use it, you can retrofit for your problem, you can solve new problem. And there are also other library that control RL integrated is to debug your system and also read your DLL file. So I think that's all from my side. And if you want to connect with me, I have provided my LinkedIn, and Cozy mentioned that I am also hobbyist YouTuber who actually makes video on knowledge management and or productivity. You could say that how to actually do knowledge management or note taking to perform or learn anything efficiently. That's all from my side. And maybe next few minutes I'll take a question. Thank you.